Good afternoon to all of you. So we are very soon going to start our 8th session, that is on visual control of robotic system by Professor L. Behra from IIT Kanpur. He is joining us shortly. Please wait for 2-3 minutes. Yes, Dr. Mehta Jiten जी कुछ आप कह रहे हैं?
नो सर.
चेक करते रहिएगा डॉक्टर बेहरा का, अगर ज्वाइन करते हैं प्रोफेसर बेहरा तो उनको प्रेजेंटर बना दीजिएगा.
यस सर.
Yes, someone wants to ask anything? Dr. Desai, would you like to say something? We can discuss. I am Professor R.P. Tiwari from MNNIT Allahabad. So tomorrow the session will start at 9:30. Tomorrow we have 4 lectures. The schedule is very tight. So please be on the time. Yes, please.
Professor?
Yes, sir.
Some people, they are putting unwanted things in WhatsApp group. Please check, sir.
Yes. Jiten ji?
Yes sir.
Remove that unwanted things from the WhatsApp group and restrict them to not just during the session. We will give them facility to send their queries. Otherwise, we will keep the message for our message posting.
Okay,
After
sir.
the session, we'll keep the WhatsApp group for posting our messages only.
Okay,
you
sir.
make such kind of restrictions in the group.
Okay, sir. Okay, sir.
And you delete all unwanted things.
Okay, sir.
And during the session, it is open, but after that you restrict the other things. So no one can post the message except the administrators.
Okay, sir.
This they are posting in the robotic group.
Professor Behra.
Yes.
I am Professor Tiwari from MNNIT. Am I audible, sir? Am I audible, sir?
Yes.
Yes, sir. So I will make you presenter, na? First, I will make you presenter, then we will start this session. Yes, sir. Now you can share your slides, sir. In the meantime, it's a pleasure to me to introduce our session 8th speaker, Professor Lakshmidhar Behra from IIT Kanpur, who is going to deliver a talk on this visual control of robotic system. Before inviting Professor Behra, I would like to give a brief introduction about Professor Behra. Dr. Lakshmidhar Behra is working as Poonam and Prabhu Goyal Chair Professor at Kanpur, IIT Kanpur, Department of Electrical Engineering, having research and teaching experience of more than 25 years. He has received the BSc Engineering and MSc Engineering degree from NIT Rourkela in the year 1988 and year 1990 respectively. He received the PhD degree from IIT Delhi in 1996. He pursued the postdoctoral studies in German National Research Center for Information Technology during 2000 to 2001. Previously, he was assistant professor at BITS Pilani during the year 1995 to 1999, and as a reader at the Intelligent Systems Research Center, UK, during the year 2007 to 2009. He has also worked as a visiting researcher cum professor at FHG Germany and Zurich, Switzerland. His research work lies in the convergence of machine learning, control theory, robotic vision, heterogeneous robot platforms. He has received more than 170 million research grants to support his research activities at IIT Kanpur. He has established industrial collaboration with TCS, Nissan, Bell, Bangalore, etc. And one more is Abu Dhabi company, while making significant technological development in the areas such as robotics-based warehouse automation, vision and drone-guided driver assistance system, and drone-guided pipeline inspection of the refineries. He has published more than 280 papers in the journal and conference proceedings. He has supervised 19 PhD theses to completion. He is a fellow of INAE and senior member of IEEE. He is a technical committee member on IEEE SMC on robotics and intelligent systems. His research interest includes intelligent control, semantic signal, music processing, neural networks, control of cyber physical systems, and cognitive modeling. So now I would request Professor Behra, please, sir, deliver your expert talk. Visual control of robotic system. Professor Behra, please.
Are you able to see my screen? Are you able to see my screen?
Yes, sir. Yes, sir. It is visible, sir. Visual control of robotic system.
Okay. So,
yes, sir.
Okay. Thank you, Professor Ravi Prakash Tiwari ji, and all the participants in this workshop, and giving me an opportunity to speak on the topic, the research that is going on in my lab here. Basic area in which we work is cognitive robotics. What is cognitive robotics? It's two. One is science of robot, the other is science of cognition. And how do we combine it? Then I am not going to speak on this a lot because today's topic is simply visual control of robots. So I'll focus on that more, and if time permits, then I will speak on the elements of cognitive robotics. So we have, you can see here, this is a robot in my lab, and this robot has a Kinect camera. It has been given a list of items it has to pick from this rack, and so this robot takes this snapshot, and there is a GPU server in which RCNN based visual perception algorithm runs, and based on that it detects from the list of items where is the item in this boxes, and then collects. Of course, there are many other things like motion planning, the visual grasping. Once you find the 3D model of the object, you have to create a 3D model such that the suction gripper can go exactly to the point where it will grasp the object. So there are so many things involved in this, and so you can see here that this. Can someone mute everyone, because I don't want to be distracted. So the so here the objective is that there are many warehouse automation like Alibaba or Amazon. They deploy such robots in a massive scale, where they, they have a transaction millions per hour, so they do, and it is not humanly possible to achieve it. So robots are being employed. So although here you can see this robot can replace a human being conveniently, but it's not a human. So this is what is called weak AI. So what is human? So that's again another topic. If time permits, I will talk about. So now you see, if you have a warehouse automation, these are the total building block. So you have a robot, and then there is a vision system. From vision system, you collect the data, and then using those data, you do object detection localization. And based on that, you have to do the pose estimation. Pose estimation means where the suction gripper or finger gripper has to go to grasp the object. Then inverse kinematic solution, and you can also add dynamic moment primitive based learning from human demonstration. Some of the things that I will talk a little later. And finally, you have to have a closed loop vision based grasping. Okay, so there is a, and this also I will talk a little separately. So this is just a background how to what is meaning of visual control of robot, right? So you have a visual perception model, you have inverse kinematic model, you have visual grasping model. Okay, and to make a little simpler, we may add the component like learning from human demonstration. So just to give, because this is a visual control, so I will give a little. I hope some of you know what is a robot. So you can see this is a robot in my lab from Sunk Manipulator, and this is a 7 degree of freedom robot. And this robot, there are overhead cameras. You can also add cameras to the tip of the robot, depending on what kind of application you have. And as robot joints, they move, the tip also moves. When tip moves, that manipulates the environment, 3D environment. So tip movement is in Cartesian space, and the joint movement in joint space. So that is theta. You can write here this expression. There is a relationship between, because it's a well crafted model. So there is a definite relationship between theta to x. So we can say x equal to f of theta. And when we say x equal to f of theta, we can write that by differentiating x dot equal to dou f upon dou theta into theta dot. So dou f upon dou theta is j. So x dot equal to j theta dot. That is how we get the relationship. Okay, this is called kinematic expression. So this relates the motion in the joint space and motion in the anti-factor space or Cartesian space, connected by a kinematic Jacobian. This j is normally, suppose my x is a 6-dimensional vector, that is x, y, z, and orientation of each role, and this is 6-dimensional, and theta is 7, right? So 7-dimensional vector theta. So j will become 6 upon 7. Suppose I'm only interested in x, y, z, then j will become 3 cross 7. So in most cases, J becomes a rectangular matrix. And then once you see this and effector is moving in Cartesian space, then the pixels in the camera also they move correspondingly. So there is a pixel motion u dot, and the Cartesian tip moment is x dot. So Cartesian, the motion moment in Cartesian space and motion moment in the pixel space are connected by another matrix called image Jacobian. Now, if you combine these two, you get this expression u dot equal to Lj theta dot. So obviously, we can have some model-based control algorithm, like this is simply a proportional controller. And based on this, error corrector loop, you see that this is my desired feature, visual feature. This is my actual visual feature. So there is an error corrector loop, and that goes to the controller. That gives you theta dot, and theta dot actuates the robot manipulator to reach when it's an end effector to reach a desired position, right, in the individual space. So now, just to give you a little example how this can be done, here is one. We have developed many architecture for it, but here you can see here there is a visual feature here. These are all visual features, and these visual features are fuzzified in the state space, right? And then for every zone, you define a proportional PD controller, proportional gain into error, and derivative gain into change in error. And once you have all those controller outputs from different zone, then we do a fuzzy average. This is called distributed fuzzy PD controller. And now how do we, here, what I have to design? I have to design what is my P and what is my D, depending on number of fuzzy zones, right? So what we do to do this, we take a Lyapunov function. Okay, the whole idea is that around the control loop, this Lyapunov function change should be negative definite. So red derivative of v dot would come this way, and you can see here this v dot. This is something little. How do you differentiate? How do you ensure v dot is negative definite? So you have to propose some proportional gain update law and derivative gain update law. So if you can properly estimate the structure of this and this, then you can, and then you like, and this you can see here p dot. So you can see here, robot doesn't do anything, or no machine learning algorithm does anything. Here, my PhD student, after he stuck here, then he sat with me, and then we figured out what should be p dot and d dot. So this is no machine learning algorithm can propose this kind of expression. So these expressions we get based on our experience in control theory. For example, theta dot fje, this is the innovation term, and this is this the term that talks about the how to minimize the error, right? So this is and you take this terms, and so obviously p dot should be proportional to em square, whereas because I want to minimize least square, so em square, and whereas d dot should be proportional to delta em square. So based on that, and then so this once you place p dot and d dot in this v dot expression, we can show that v dot is negative definite. In this paper, you will get all detailed information. And and once you establish that this is Lyapunov stable, all that you have to do is establish v dot is negative definite. And you can see here, after we got this law, you code it and run your robot. So here is the task is, this robot has to follow this pink ball while maintaining the distance between the pink ball and its end effector. Camera is put inside this end effector, and it looks at the, So you can see is that we have not estimated the model parameters of the robot. We simply directly tuned the proportional gain and derivative gain, and using this Lyapunov stability theory, and the robot works very nicely. So this is called vision-based control, right? Whether I showed you warehouse automation or here, these are called vision-based. That means how do we incorporate visual data in taking the action, right? This is another. This is purely grasping. How do we grasp an object? To grasp an object, for example, I don't know. Are you able to see my mobile? Professor Tiwari, are you able to see my mobile?
Yes, sir. Yes, sir.
So
Sir,
you
your
see that
voice is breaking, sir. Mic, mic is, I think, some issue. Mic issue is there.
is it clear now?
Now it is clear, sir.
Okay.
Yes.
So whenever you have problem, please tell me no, because we have no way to know whether things are right for you or not.
Right.
So kindly always give me the feedback.
Yes, sir.
So this is an object, and grasping means this is called pose, right? Where my gripper is going to catch it. This is called pose, right? So this is pose, and this is called axis. This is called pose. And catching any object, you can have many poses, right? So what we do, given a workspace, we generate some, here in this case, 15,000 different random poses, okay, with a different orientation, because we can assume that object, normally when we pick an object, we pick the object around the minor axis, not major. Nobody will try to catch the mobile like along the major axis. You will either catch like this or you catch like this, right? So this is how it is done. So we have some random poses around in the framework, in the visual frame, the place or the background in which the objects are placed, the frame, visual frame that camera takes, and then it does a filtering. That filtering is to know if there is an object, then the depth of that object will be different than the depth of the object if there is no object. So it is very easy. Suppose there is a background in which many objects are placed. So wherever object is there, depth will be less. When there is no object, depth will be more. So based on that concept, you can filter. So there is a single object here, and now on that single object also, there must be around 100 poses, because you can catch that object in so many ways. So what you do now you do a cluster. Using cluster, you figure out what is the minor axis and major axis, and there are some details by which you have to discard most of these poses except one. Okay, that is most likely. And that the same thing happens also with the multiple objects you can see in the second frame. And so this is how, and this is this particular, like in our previous, the first one I talked about. In the first one, we use deep learning network, which is computationally very intensive. Here, this is simple clustering algorithm, and you don't, in a real-time fly, this will work on any system. So you can see here, this is, please enjoy this video. So you see here, the robot is able to grasp all the objects. It doesn't do the object identification. All that it does is that it isolates one object from another, because job is simply to pick one object and put it there. So this is there in the warehouse. What happens in warehouse? Thousands of objects, they come, and robot has to place them in different boxes, right? Different racks. So it doesn't have to do the recognition, identification object. All that it has to do, it has to pick and put in a rack, and must put in the system which rack it has put in. That's it. Okay, so that's all it has done. So this is unless you go to a warehouse. I have visited during our participation in Amazon Robotics Challenge, and during that we are taken to warehouse, how objects they come, how they are put into different racks, and when an order comes from the customer, how do they, based on the system input, they know this object is automatically in this particular rack, and robot goes to that rack and collects the object and puts in the delivery package. So you are able to see that you suppose the robot is picking objects, and so this is grasping. Now I will give you a little mathematics, how we do or we design optimal control in vision-based visual survey. So you see, this is the diagram, schematic diagram. This is my visual feature. This is my actual feature, and I have a controller, and we have a critic, because when a robot does manipulate, it is important that function that must be optimized, not simply do a task, but a task function must be optimized. So if I do it using classical control, optimal control, then I cannot do real time. I have to do offline. First I have to solve it. I have to find out all control values, and then I have to implement. So this is but here what we are doing, we are doing a near optimal solution using adaptive critic. So critic gives me a feedback, how well is my control input and how well my cost function has been optimized. So you can easily see here, this is our kinematic equation, and in this kinematic equation you have this is my control law. You can see this is a control law, because we could put it into input affine system form. Then following the Hamilton-Jacobi-Bellman equation, we could figure out what should be my optimal control. But in this, we do not know what is WC. To compute WC, because this WC is the weight of the critic, so we have to find out the weight of the critic. So for that, we found a Lyapunov function, and then we derived the weight of that law, such that the entire closed loop is Lyapunov stable. So this is what we are doing, and you can also see now this is the experimental platform. So you can see in the table there are 4 books, and the robot has to arrange these books according to a pattern. The bigger book and the bottom most position, and on the top of that the next bigger, next smaller, and the smallest one will be in the top of. So this is what is told to robot, and robot has to do it autonomously. So you can enjoy this video. The robot is generating its path in optimal way. Now it is figuring out which is the biggest book. And once it figured out, it will pick that book and place in a designated area with a proper orientation. These are user defined. Yeah. So now the robot will look for other books. So next big book, it will go. There is a continuous feedback of visual feature, and there is an error corrector loop between the real visual feature and the visual feature that are being seen, and then that error corrector loop is driving the robot to reach the goal position, and then it goes and places exactly on the top of the first book in same orientation. So you saw the next big book was picked and again placed, and finally the smallest book. Of course, here you can see that there are books, but why there are some Aruko marker. So the reason here we have used Aruko marker because we don't want to do a system identification, sorry, image object identification of the book. That we, of course, you can always do a, then visual perception algorithm has to be incorporated. So to avoid that, here we are simply demonstrating the control efficacy, and that is why Aruko marker is given, and Aruko markers are very easy to identify. Okay. Is my voice now audible?
Yes, sir.
Okay, so so this is a little bit of the direction in which the robotic research is going on as of now. You know that in this figure you can see how we have grown from a single cell to now trillion cells, and we have grown both in terms of hardware as well as software, right? So as a human individual or any biological organism, they grow like that. And unfortunately, all AI and robotics, we may speak very big. We have not even scratched the surface because we don't have any knowledge how a robotic hardware can grow. Like, can I say a father robot will give rise to a child robot? We don't have that concept, and so this is and nor we have seen evolution of emotion, intellect. Can a robot with simple concepts can learn what is Lyapunov stability theory, and given a system, it can figure out what is the Lyapunov function associated with it, and then it can derive what is the control law, such that the derivative of the red derivative of the Lyapunov function is negative definite. So we are very far away from the cognitive cognition of a human being or cognition of any biological organism, because each biological organism has cognitive ability, from bees to insects to earthworm to the birds, animals. They always do that. So there are, you can see there are, I have given some link, and these links show that there are some group, they are working on cognitive robotics project, and those who are interested, they can go through this slides. So what you are seeing here, that normally all AI is all AI methods are simply pattern. There is no meaning. We do not manipulate the meaning. We manipulate the syntax. Okay, the pattern. Like for example, the first one, face recognition by Zhao et al. In 2018. You see, you give certain pattern to the deep network, and deep network is going to reproduce a pattern. And in this process, the meaning is provided by the researcher. The researcher defines what is an objective function, and researcher also collects the data, and data has to be collected such that ground truth is assigned, and then the researcher has to design the learning algorithm. So whether it is face recognition, speech recognition, we deal with the data in a syntactic manner. We don't have understanding of what is meaning. So that is the great bottleneck. So if you look at cognitive approach to human development, we have one concept called self-awareness, right? Even a child, when is born, he knows how to suck the breast of the mother, right? A child, when starts crawling, he looks, or he or she looks for an opportunity to crawl. Just like I have told many times about my own daughter. When she started crawling, in our house we had a staircase, so she would always go towards the staircase to experience the thrill of crawling. And although we were watchful, but still she knows when we are not watchful, and she would simply go. We down many times from the staircase, because this is a innate ability of a human or any biological organism to become self-aware. We don't have any machine that is self-aware, or for example, world awareness, right? And imitation. I will show you some imitation, but the imitation that happens within biological organism is in a meaning level, semantic level, not in syntactic level. So these are all very higher level principles, which I am not going to talk. But now let us go to the next topic, that is imitation learning. I had given in that warehouse automation, one is learning from human demonstration. Again, as I told you, the way we make our machines to learn is completely different the way we learn, because we are aware of ourselves, aware of the world around us, and we learn from semantics, and we are hardly aware of the data. Okay, it's the meaning that drives us, not the data. Whereas the current AI and robotics research are data driven. You have data, then you can do it. It's from syntax, and the meaning is incorporated by human being. So the, like for example, the intention, given an intention, can a robot act? So for a robot to understand what intention is, a very tough thing, or we don't understand actually. So that is the even bigger problem. We don't understand how we act according to the self-awareness or intention. So here, what you are seeing is a scheme where a teacher, Kathak dancer, is going to teach a robot to dance. How can we accomplish it? Obviously, when you go to a dance teacher, you learn from demonstration. The teacher explains the concept and you do it. And when teacher accepts, you don't look at the data, you look at the concept. But here you will see we are doing data driven. What we do, for example, a Kathak dance can have many primitives like bandhana, that, salami, and these primitives can be captured based on visual patterns, auditory patterns, and these patterns are, once they are collected from the dance sequences, then we have to put an AI algorithm to categorize those features in terms of moment primitive 1, 2, and until k. And then we have to write another AI algorithm given a dance form, how do these moment primitives should be ordered, and this moment primitive, how they get synchronized with the joints of the robot. And then you see that now the robot would start dancing. So this is how it's purely data driven. It is computationally very intensive, and unfortunately this is the current state of AI. So I will just to give you how we do. Okay, so there is some issue here. Yeah, okay. So you see here is a demo. This is called demo. There is some issue there. What happened? I don't know. Okay. Okay, you see there now. So here my student is giving a demo to the robot. Robot picks the object and places in the proper box, designated box, and once that demo is given, robot should be told you follow that. There is some issue here. So you see, once demo was given, now robot goes and picks the object and places in the desired place. So this is called by demonstration. You learn by demonstration. Now I will give you another example. So you see here, the two students are teaching a robot how to hit a ball. And then once you collect those data, you create the learning model. There are so many things. It is not simply hitting the ball. You have to track the ball. There are so many algorithms. I'm not going to go in detail. All that I'm talking is that how the robot can hit the ball from the middle of the bat. So you see that robot is not doing a good job here. So we have to teach the robot more. So more examples are generated, and the examples were not sufficient. And then you see here, this is the so you see here how the robot can hit the ball, and you see that ball is coming from every direction because it is freely hanging. It's a very, very difficult problem. You have to track the ball and you have to hit the ball. So there are so many algorithms that have to perfectly work in coordination with each other, and then the ball, robot can hit the ball. So I hope, but just to do that, it is not an easy thing. Just simply to hit the ball, the data that were collected that have to be put into a specific model. Here it is a stochastic regressive dynamic model. And because the robot has to generate a stable behavior, so you have to add a control signal, and that control signal has to be properly generated and in such a way that the system will be stable. And for that you have to take a Lyapunov function and so many things you have to do. I'm just omitting it just to let you know that there are these tasks to do. You have to be equipped with the system identification. You have to be equipped with the learning, stabilizing the model, and so many things, right? So I will not go in detail. So those are all necessary. It is not. So now I will give you a little background on how a robot can learn how to play a tennis with a human opponent. So you can see here is a robot, is a human opponent, and how they will play. So here there are two things. One is lower level control, where robot is going to hit, and the higher level control, where robot is going to plan how to hit. So for that, higher level skill is done by reinforcement learning, and lower level skill is done by human demonstration. So this is for higher level skill. We look at the system in terms of environment, agent, number of states, different actions, and finally reward. If robot has properly hit the ball such that the opponent is not able to return, then he gets maximum reward. And if there are rally, the duration of rally, for example, the robot hits, the opponent returns, and then hits and returns. If the rally is long, then reward is less. A rally is less and it wins, then reward is more. So these are the concepts by which we learn. So these are, you see, you create a state space of this entire action. What is the absolute position of the agent, absolute position of the opponent, absolute position of the center of the table, elbow position of the opponent, absolute bounce position of the incoming ball, absolute velocity of incoming ball, absolute velocity of the opponent, and like that. You have to understand everything. That means you have to reduce the entire semantic environment in terms of some syntax. And then you see that so for example, this is your agent. So agent has to hit. So the other side, the opponent's table side, is divided into, you can see here, 4, 4, and 4, right? Or here it is simply 4 and 4. That is 8. So the agent can hit the ball here or here or here or here. So 8 different places, right? So how it will decide? It decide based on where is the opponent. Suppose opponent is here, it will hit here. Okay, if opponent is here, then it will hit here. So some kind of things, but it has to be learned, right? It has to learn that this is, we know but from our experience how to hit. And then where it will hit. So this is the plane of hitting. In this plane of hitting, there are 9 different zones we have done, and it will hit in one of those strike point. These are the strike point. You can see there are 9 strike points, and the robot can go and hit the ball. And that means the robot is going to intercept the ball in this. So basically, if you look at this the entire concept, there are vision system, higher level skill, where you have the action taken by the agent using PQ learning. There are so many reinforcement learning. It is not necessarily only PQ learning, but we have employed PQ learning. And then there is a lower level control from human demonstration. Once you have planned and you know where to hit, then how to hit, right? So this is so you see, I'm not going to give details here, but just to give a concept, how do we, what is moment primitive, or how do we learn from human demonstration? All of you know that mass damper system. So this is a mass damper system. What is a mass damper system? You go here, a mass damper system, if it is critically damped, so this is a mass damper system, if it's critically damped, then from position A to position B, which is the blue curve, position A to position B, right, in the first figure. So it will go straight, right, and critically damped. Similarly, in the second figure, similarly, you can see that how this is the position and this is the velocity, right? So velocity will increase and then it will decrease because it has reached the target. So this is a mass damper system. But normally, suppose there is an object. So there is an object, and this object has to be moved, right? There are two objects, and this object has to be moved the other side of the bottle. So I cannot go and collide with the bottle. So human demonstration is that there is a bottle, so it will go like this and go to this side. So this is called human demonstration. So human demonstration takes into account a path constraint, other objectives, and but how can I get a shape of my trajectory instead of this, the red one, right? How do I do it? So to do that, we add a forcing function fz, and the forcing function is parameterized in terms of certain parameter wi, and then we have to update the weight. Okay, so this is what is a demonstration from it's a learning from the human demonstration. And then you have some cost function, and this cost function is minimized, and we have this weight update algorithm. This weight update algorithm we have taken from our own work published in IEEE transaction neural networks. So this and then you can see that whatever we desired, we followed, we got it, right? So this is I will not go in details. So this is the same learning to hit the ball, but in a more compact way. There are two things. One is higher level, in low level programming and demonstration, there are two things. One is kinematic control, the other is the dynamic control. So you can see here Ravi is doing a demo. So this is a Barrett arm, and Ravi is giving a demo to the robot. So this is hitting. After hitting, the robot has to go to the home position. So this is called the second demo, how to come back. And like that, he would generate some, not more examples, very minimum example, like around 10 examples, 10 times hitting. And then once he collected those data, he learned those mass spring damper system with the forcing function, those parameters, and robot is able to learn it, how to hit the ball, right? So this is the programming by demonstration. Using programming and demonstration, we can do many things. that normally humans are capable of. So this is another work. I will not go to the details. I will just show you the video and I will explain to you what this is doing. So you can see this is a part of the work is in ICRA 2019 in Montreal. The previous work was published in Control System Technology. And so here the objective is that this robot has to localize some piles of brick. It will take those brick and make a brick wall according to a pattern. Okay, so you see here how this is being done. So there is a magnetic gripper. Using that, it is lifting the brick, and then why the brick is put in here, because this magnetic gripper, while going, because of the uneven surface, it may the object may fall down. So the best is that you collect these bricks and carry it in your body, and then when you go to the place where it has to be put into in the form of a wall, that time you pick it and then you place it. And this has to be done according to a given pattern. So pattern is given previously. So you see here that so one is understand where is the brick pile. So vision-based pile localization has to be done. Once it is done, then it must go and pick one of the brick. Okay, so that is grasping. And once it goes, it has to make a proper plan how to go and reach the destination spot. And there it has to go and using proper kinematic control, it has to place the brick in a proper place. So this is the total. It looks very simple, but to implement this is very. It's not an easy, because 3-4 PhD students combinedly they performed this task in my lab. This is a preparation for a robotic competition. Okay. So now I will just digress a little bit to explain how much time I have. Okay, so I will take not much time. I will.
Sir, you can continue. You are having sufficient time, sir. Half an hour. Half an hour more, sir.
Okay.
Next lecture will start at 5, sir.
Okay. So this. So what you can see here. We have to have a brain-computer interface. Just a moment. So they cannot hear the video. Something has to be done, right? Mm-hmm. What is done? This give control.
We can play VNC in our system.
Why? Now, if I play, they should hear, no? Are you able to hear?
Yes, sir. Yes, sir.
You are able to hear?
Yes, sir. Yes, sir.
No, no, this video, audio, you are able to hear?
No audio we are not able to hear, sir.
Now I'm playing. Can tell me. Are you able to hear?
No, sir. We are not able to hear the audio, sir.
I think this Abhishek Jaiswal was doing something to do this. No. Okay, so let me check if I can directly play from here. I think this one. What? Where is the... This one. Yes, I think I do. Share. How I share? So, yeah. Huh? And then I have to come out, right?
Yes, sir.
And then I have to go where? I will share the screen. Let me share the screen. Where is the screen?
The screen is not there. You have to play the video again.
Huh?
Play the video again.
So, no. Yeah. Where? Where is that? Yeah, this one. No. Yeah. No, it is not. Asani, this Abhishek Jaiswal knew how to do it. Something came now. Yeah, I go. No. Where is that? Oh, I know how to do. So, this is... okay, so what I have to... This one, right? Imitation learning. This is what I have to go. Are you able to see my screen now?
Sir, yes, sir.
So, are you able to see? Are you able to hear now?
Several PPTs are there.
No, are you able to hear now? Playing something, are you able to hear?
No, sir.
जायसवाल को पूछ रहे कैसा होता है he did it actually. You are good for nothing. जा जायसवाल को पूछो. What are you doing? हाँ there is nothing like that. When you don't know, why you are wasting my time?
The app, once if we just add this folder. So where is that thing? This folder.
This is not the way it has to be done. It is just. Are you able to see my screen now?
Yes, sir. Yes, sir. Screen is visible, sir.
This drowsy driving, are you able to see?
Yes, yes. But that screen is not coming, no? Drowsy drawing folder is showing. Now, yes, now this is coming outline. Yes, sir.
Are you able to hear now?
Yes, sir. Video is playing, sir, now.
And you are able to hear the audio?
No, sir. No.
Okay, so what I do, I'll come out of this. Sorry for the, I had a student who knows how to do it and he's not here. And I thought I'll be able to manage it, but let me check another. Okay, so let me see whether I can do a justice. So you can see here, what is a brain-computer, brainwave controlled robot? In a brainwave controlled robot, you see, you can see here, this is a student. This is a person who is sitting in a wheelchair. He is simply thinking to navigate in this entire room. Sometimes he wants to watch a TV. Sometimes he wants to turn on a light, or sometimes he will go and want to drink some water. So simply by thinking, all these appliances are connected to his brainwave signal, and they work. So this is what is brainwave control. That means why brainwave control has taken a big leap, because you might have heard about Steve Hawking, who was actually a motor neuron patient, and he was completely in wheelchair almost from the age of very young age, in 30s. And motor neurons are those neurons that actuate our muscles, so that we can lift our hand, move our leg, make some facial expression. But unfortunately, because all his motor neurons were dead, so only very few were alive, and that was able to make his lips move a little bit. So whenever he wanted to read something, that intention was mapped to his lip movement, and IBM created a synthetic speech system for him. So although Steve Hawking was reading or speaking, but it was actually synthetic one. Okay, so so I will just tell you another kind of network that we used for our brain-computer interface. This is called quantum neural network. And in this quantum neural network, what is interesting in this quantum neural network is that you have a neural lattice, and when you excite these neurons, there is a collective response. And what is this collective response? This is called superposition principle. This is there in quantum mechanics, like these are all different slits. Each slit is associated with the wave function psi1, psi2 to psi n, and the collective response is psi equal to c1, psi1 and cn, psi n. So this is called collective response model. So that is, we gave a proper framework of neural information processing by which the robot, they can the brain information processing can be explained. So one of the things that we did is, using this model, we could recognize a signal, and as we separate. When, for example, when you do brain-computer interface, your electrical activity is happening inside the skull, and then there is a skull. So when you get all these electrical signal, you don't know what kind of signal you are receiving, what is the noise, what is the actual signal, and the source of noise we don't know, the shape of noise we don't know, the signal type also we don't know. So when we are faced with this, so we thought, let us apply this quantum neural network to the brain computer interface signal processing, or brain signal processing, or EEG signal processing. And what was the objective of this whole thing was that quantum probability is a probability that automatically evolves based on how you modulate the potential field. Okay, so what we did, we modulated this potential field using an error corrector loop, and I will explain that a little later. This is exactly what we have done. So these are all neural network parameters. This is the Schrodinger wave equation that is activated. So I have an activation function called Schrodinger wave equation. And then you get a psi function, and that psi function, based on psi function, we get a maximum likelihood estimator of the signal. So my Y is a signal embedded in noise. I do not know what is Y. I do not know what is noise. I only know noise plus signal. Now, this particular thing was able to help us to extract the signal from the noise, right? So this is something, towards semantics, towards next level of semantics, right? This is exactly the Schrodinger wave equation. These are the different parameters. This is the learning algorithm for K using Hebbian learning, and this is the maximum likelihood estimator. And finally, how do we do the integration of Schrodinger wave equation? And you can easily see here, there is a signal that is embedded in 20 dB noise, or here it is 0 dB noise. Okay, so you can easily see here the quantum probability is able to track different signal values. We assigned a zero mean Gaussian PDF to the Schrodinger wave equation, and then that PDF slowly modulated itself until it reached the destination. So this is like a particle, a quantum particle with a amplitude is moving. And this is what we demonstrated in different kind of signals. I'm not going to give in detail. Let me go to the BCI, brain computer interface. So we have two kinds of signals, and then we put these two neural networks, quantum neural network, and then based on that, C3, C4 was the signal with noise, C3 cap and C4 cap is the estimated signal, and then we did a feature extraction. Mostly we use Hort feature, and then a simple linear discriminant analyzer. So this is a linear classifier. So, and this is the detailed operational block diagram BCI that we did, and you can see here. So this is this is so you can see here there is a robot. That robot is moving according to the thinking of the person is deciphered in terms of left movement, right movement, backward movement, forward movement, so like that. And based on that, you can see this robot is moving in its space. So this is a proof of demonstration that we did. Now BIRAC has given us some fund to actually take this proof of concept to a industrial product, where we will have a wheelchair, and a person sitting there in the wheelchair can think, and it is not only motor neuron patient, stroke patient, mental patient, so many people who can think at least left and right, binary thinking. As long as they can be trained in binary thinking, they will be able to do their daily activities without much help from others. They should not be too dependent on others for their daily activities. That is the main objective. Okay, so these are some of the publication there. I'm not able to show you so I'm not able to show you the one that I wanted to show you. Let me now.
Systems sound settings में sound control
जाओ. And then what happened?
If you want to share the video from that films thing.
No, it was playing from here only.
From films thing, we can do this and we can.
I don't know what you are doing. I think that doesn't work. This is Abhishek Jaiswal only knew. Here it is.
Hello everyone.
Are you able to see that?
Yes, sir. Now it is coming, sir. Hello.
You are able to hear the audio?
Yes, sir. Yes, sir.
Okay.
Now voice is not coming, sir.
No, my voice not. This
No,
voice
no,
is coming.
video voice is not coming.
Chalo. Sorry, I am not able to solve this problem. Let me go and okay, so I will stop this part. I'll skip this part because this is anyway. You see that the brain wave controlled robot. So there are. I explained to you what is a brain wave controlled robot, right? So this is we are doing now. I will not speak. I have spoken this. We are also doing brain of signal P300. We are using P300 signal to detect the intention. Suppose somebody has done a crime, and we don't have to do investigate, or we don't have to ask him anything. Simply, if we can show some crime scene, and if he has done that crime, then there will be P300 will be activated. And we have developed an application, 6 months back, we demonstrated this CVI on this application. So with P300 application, a lot of security stuff we can do, and that's what we are doing. Okay, now I will come to the end conclusion. So what I did is that we talked about the machine learning and robotics and brainwave controlled robot and other such application. But unfortunately, as I have told you, everything the researcher does, and then hard codes in the machine. So you see that there is a hard problem. Suppose so all that we do, we solve is weak problem. What is the hard problem? The robot. Let us think of it in terms of a thought. A robot comes and lives in your house, and hears your family members, picks up vocabulary slowly and steadily, and let's say start speaking in a broken language. You are from Allahabad, so let it speak in Hindi and becomes expert in your language, like let's say Premchand, and then learns to write poetry and receives a Nobel Prize in literature. If the robot can do all these things gradually the way we do, we can say, okay, we have solved the hard problem of AI, but it is a far off goal. We have not done much. And just to explain how this can be solved, we have to take a semantic approach because modern science doesn't understand what is an experience. We all go by experience, right? And our experiences are the convergence of two things. One is the object of experience, the other is the detection, and the third is the space. And the space is, we have 5 different space: sound, touch, visual, taste, and smell. And so this particular thing, we are trying to develop this thing. So if you look at the current physics and semantic physics, in current physics, your primary properties are syntactics, like x is position, t is temperature, and secondary is the emerging properties. They are interpreted as meaning by the external body, like a human or a computer algorithm, like visual space, face or painting, auditory space is music. So these are all secondary. So in case of modern science, painting or face, human face or animal face or a music, these are this cannot be described by modern science because they are simply emergent property. Okay, so that is why no notion of meaning It is just data, right? So this syntax. Whereas in semantic physics that we are trying to work on, semantic space carries the meaning. So position, a property in visual space, temperature, a property in a touch space, and secondary properties are mass, time. These are all derived. So whereas in current physics, mass and time are primary property. So this is a little misnomer, and this is what we are trying to. So just to give you an idea that every living organism, they are born with a specific universal semantic space, and that semantic space grows as the individual or organism interacts with the environment. So that's why environment plays a very important role in the development of a personality. Somebody is brought up in an intellectual environment, he will be tending towards intellectual pursuit, whereas somebody is brought up in a business environment, he will be tending towards a business profession. So this is, we have seen, we notice, but current science doesn't know how to deal with this. So this is, I will stop here. So the conclusion is, why must we build a human-like robot? It will help us to understand gross sensory level perception, its connection to emotional and intellectual construct, which is you can't do in modern science. May lead to environmental friendly science and technology. All of us, we are completely disturbed with the COVID pandemic. A simple virus has completely punctured entire economy. The people are locked inside. There are so much of depression, and this is undesirable. We have airplanes, they cannot fly. We have trains, they cannot fly. We have labs, they cannot run. So this is not the kind of science and technology we are looking at. So we must now think fundamentally differently. That will also give us sustainable and synergetic development of the human society and more meaningful connection among people, not like these inanimate gadgets that spoils our children, ourselves. There are many people nowadays, they can remain in fast for a week or a month, but they cannot fast from a mobile application or mobile phone or laptop or this or that, even for 5 minutes, 10 minutes, what to speak of a day. So there are many bottlenecks that needs to be looked at. One thing that AI has done, AI has brought in, is that I'm going to speak another lecture connected to this, is conscious driven machine. We are conscious driven machines. So human beings are not like animated machine. Human beings are conscious driven machines. So what is that consciousness? That is something fundamental. I am going to give a talk on that, I think 6th or something, that Professor Ravi Prakash will let you know. Thank you very much. I stop here.
Thank
If
you
you have
so
any
much.
question, if you have any question.
Any questions, please? I would request all the participants, you can ask questions. Any questions, please?
Okay, so if there are no questions, then we can conclude. We can stop here this session. Okay, Professor Tiwari. Hello.
Sir, he is on call right now, I think. Okay,
So
sir, we
then,
can leave, sir. Okay, sir,
yeah,
we can.
we can end this session. Thank you very much.
Thank you very much,
Thank
sir.
all
Thank
the
you very much.
participants for hearing. Thank you.
Thank you,
Thank
sir.
Any question, please?
Sir, he has left, sir.
Huh?
He has left, sir. Because there is no questions from the participants.
Okay, okay.
Yes, sir.
We have another lecture after 10-15 minutes.
Okay, sir.
ठीक है जितेंद्र जी? हाँ?
Sir. Yes, sir.